Los Alamos National Laboratory and also Oak Ridge National Laboratory in computer science, technical and administrative roles with a technical focus on communication libraries and application analysis tools. So he's also a co-founder of the OpenMPI collaboration and was chairman of the MPI 3.0 standardization efforts. So today's tutorial, he will be presenting on the NVIDIA DPU Collective Offload. So let's welcome Rich.
So thank you, and thank you for the invite. Can you hear me?
Yeah.
Can you hear me for this? Okay, I just wasn't close enough. Yeah. So thank you, and thank you for the invitation to talk here today. What I'm going to talk about is work that we've been doing in my team within the last year and a half or so in terms of trying to take advantage of what we call the data processing unit, NVIDIA's data processing unit to offload collective operations specifically. So I'm not going to show any slides on performance. Most of the talk is aimed at really talking about what the capabilities are, some ideas on how to use the capabilities and the like, so that people that are interested in this sort of work, and I assume and I know that in this audience there certainly are these sort of people. That you maybe learn a few more things about a few more capabilities, or maybe a few different ways to think about it that might be useful at the end of the day, in terms of work that you're doing. So I'm not going to show results, not because they're not good, not because we're trying to hide them. It's just not the point. So I just didn't put them in because they weren't in the previous slide deck that I started from. Anyhow, so the results are what one, or actually more than what one would expect. So as I said, what I'm really going to focus here is on using the DPU for two reasons. One, to improve application performance. That's really the #1 goal here. And that drives decisions that are made in terms of how one designs algorithms. That drives the sort of things that you think about in terms of capabilities that you may want to leverage. And a lot of the goal here is to move, to the degree that it makes sense, to move management to the collective operations to the DPU. Okay, so management is the focus, not moving data to the DPU, although that is relevant for some algorithms. So before I start going into some of the considerations in terms of designing algorithms, I want to give a bit of an overview of NVIDIA's DPU, the Bluefield unit. Actually, it's the Bluefield family of devices. And so today, we're at generation 3 of Bluefield. We're Bluefield 3. So we had the original Bluefield, which I'm not even going to talk about, was not intended at all for HPC. It was intended mostly for data centers, for hypervisor storage management and stuff like that. Bluefield 2 is a device that most people have had access to recently, for the last several years, and recently Bluefield 3 has become available. So what Bluefield is, it's a system on a chip. So that chip contains several units. So this is part of both our Ethernet and our InfiniBand technology. So what it includes, one of the units is the network core. So for those of you that are familiar with ConnectX, it has a ConnectX core, and that core depends on which generation of technology you're working with. So in Bluefield 2, the core is a HDR core, and in Bluefield 3, the core is an NDR core. And we'll talk a bit about what that means in terms of speeds and feeds soon. So that's one piece of the device. The other piece on it, the other part of it is there are user programmable ARM cores on the device. So you have in Bluefield 2, it was an A72, in Bluefield 3, it's an A78. So you have some computational capabilities that are typically used in HPC. So you have floating point capabilities as well as integer capabilities. You have a memory subsystem. You can use your standard GNU or whatever compiler tools to create binaries for this. It runs an OS, some version of Linux, so there are several versions of Linux that are supported. So it really is an environment where from a user perspective, you don't have to go and learn how to program an FPGA or some other device to be able to use it. You can basically use the same way you program for using the host in terms of communication management or other capabilities that you may want to use it for. You can use that same skill set to start putting code on the DPU. But it does require thinking about what you're going to do, because it's easy to do something that doesn't make sense and harm performance. So you need to think very carefully what portions of your workload you want to put on the DPU and what you want to leave on the host side. So there are a few other acceleration engines that exist on the device. There is some compression or decompression capabilities. There's a regular expression engine that's very, very fast. Again, some of these are really targeted more for security, and originally were targeted for security and storage, and so there's certainly capabilities there, added accelerations on that device that exist there. And so if you can figure out ways to use those for some of the algorithmic work that people are interested in, that's certainly a way to go. I will say this is a general purpose processing element. Depending on your addressing mode, you could run your MPI on it. If you run your MPI on it, you better be careful, because it's a weak processor compared to the host. So don't put too much work on that device, on that unit, or you'll be very sorry in terms of performance. So you need to think about what you're doing. You can do. Other people are looking at it in a variety of areas. Some people are looking at it, actually within my group, at using it potentially close to storage to do some quick data queries and stuff like that. People are looking at using this device for telemetry. And of course, it's used in the data center for hypervisors, and it's used. One of the use cases is security. A big use case for it is security. So there are a lot of potential uses here. But my focus today is going to be solely on optimization of or porting of collective communication to this device. So that's the hardware side of it. On the software side of things, there's an infrastructure we call DOCA. It's data center on a chip architecture, if I remember correctly what DOCA stands for. It supports both Ethernet and InfiniBand. Ethernet is ahead of InfiniBand in terms of capabilities. So there's some basic capabilities that one can use there to help in the process of putting code on the DPU. So the way we tend to think about Bluefield at NVIDIA, this is one of the ways to look at it, is if you think in terms of a system perspective. From a system perspective, you have the traditional host, where the host is the center of everything. You know, it runs the application, runs your security, it runs your progress for your communication library, it does everything, right? And so you have to share the resources on the host to be able to run a full application. The NIC is something that's sort of attached. In our case, it has capability. In the InfiniBand case, it has capabilities, computational capabilities, and communication management capabilities that exist on the NIC, but mostly they're two different worlds that communicate some between themselves. So with Bluefield specifically, a big goal with Bluefield is to move as much as possible of management capabilities, not just communication management capabilities, offload it from the host to the DPU so that the host is left for computation. So people spend a lot of money on buying very powerful computational engines, whether they're CPUs, GPUs, other things. Want to leave that for computation. They're designed for computation. Want to leave that as much as possible for computation. So this is a perspective that that we come from in terms of system architecture. And so slowly keep some of the management capabilities and associated with a cluster with your system are being moved down to the DPU. And so what I'm talking about specifically today is moving management of collective operations to the DPU. So if for those of you that are familiar with InfiniBand, you know that the sort of philosophy that we have in our network design is to move capabilities, as much capabilities as we can in terms of network traffic management from the host to the DPU. So we spend a lot of hardware doing these sort of things. So we have support. You see the list here of things that we support. Things like RDMA, GPU Direct RDMA, GPU Direct Storage, adaptive routing, congestion control, which actually has part of it's done by on the NIC, and other things that help us get low latency, high message rate, and high throughput. So this is the general philosophy that we have, and in terms of the DPU, if you see here on the right, on this figure here, from a communication perspective, some of the protocols that we offload to the offload from the host prior to the DPU, Sharp as a data reduction, that's certainly been already offloaded to the switches, not to the HCAs. And this gives us the ability to be a lot more flexible in terms of how we offload other parts of the communication stack to the DPU. And again, I'm focusing today on the all-to-all. I'm sorry, on the collective operations. So now I'll get into a bit more in terms of how we think about offloading work to the DPU. Offloading collective management to the DPU. So if you think about your host-only model, when it comes to communication, and I'm specifically talking here in the context of UCC, which is an open source collective library, parallel to UCX, for those of you that are familiar with UCX. And I'll describe a little later what UCC is. But the way host-only model works is all your MPI activities happens within the context of a user process. And in MPI, it's an MPI process. It doesn't have to happen like that, but in practice, that's how it happens in MPI implementations. So everything that happens in terms of management of collectives happens on the host. And when the host gets a chance, and when that library gets a chance to make progress, and what that typically means, that happens when an application makes a call to some sort of MPI function, whether it's initiating some sort of point-to-point collective, whether it's testing or waiting on completion. That's when the communication or collectives can be progressed. So on the DPU offload model, the way we view it, this is not the only way to view it, but the way we view it is we view the DPU as an extension of the host. So we're not trying to put additional MPI processes on the DPU. Personally, I don't think it makes sense. Personally, I think it's a very hard problem. If you're going to do that and get improved performance, it's probably a losing battle. But we view the we view the DPU as an extension of the host. So both you can make progress on a collective operation in calls from the application into the MPI library, or you can also make in the background progress on the DPU. Yeah, so the DPU, all the DPU is doing from a collective perspective is just progressing communication. It's not competing with anything else. And so a few things to take into account when it comes to design considerations. So the first thing we have here is we have an entity that's really asynchronous, right? You have basically a processor. I'm not talking about any sort of extra accelerations that you might have on the DPU, just in terms of the ARM cores that exist there. You have a processor that's always available to perform, to be involved in the collective operation. It means you always have an opportunity to do something with collectives. That means that you have opportunities to do things that you cannot do with host-only operations. So you can be very, very reactive to runtime, actual runtime situation in terms of the collective operations for progressing them and for getting, and actually to take advantage of this, you really need to redesign your collective operations, not in big ways, but in ways that have a big impact on performance. And those are the ways that we go after them. And I'm not going to talk about our algorithms. We've actually patented them, and we don't share them publicly. But I'll certainly give the key ingredients that we use, and one of them is this asynchronous ability for asynchronous progress. Another thing to take into account is the fact that even though you do have this asynchronous agent, you typically have a lot less computational capability or computational elements, and that's where you get your parallelism on the DPU relative to the host. So I like to think about it in terms about a 10-to-1 ratio. So you need to be careful in terms of how you try to use this, because in essence you have, you know, on the host side of things, if you had 10 processes, each of them independently progress their collective operations. Now you have one process on the DPU that has to progress everything for all those 10 MPI processes if you're using MPI. And so need to make sure that is first of all, that is a serialization bottleneck, and so you need to make sure that you minimize that serialization bottleneck. So that needs to show up in your algorithms and in terms of what you try to do algorithmically. But it does have the advantage that because one process is progressing communication for several other, in this case MPI processes, you have a better global view of traffic in your application, and so you have an opportunity for optimization that you do not have in your host-only algorithms. Now you could create that in your host-only algorithms, but it would require additional resources, and it would harm your performance. So this is something that we've seen firsthand. Certainly helps us. So a lot of our work so far has been on managing larger message sizes, ones that are relevant, for example, for weather applications and the like. And we see that capability helps us in the larger message sizes to get better latency performance than compared to host-only algorithms, right? Because we're not overwhelming the network by having too much work being given to the network, causing issues with congestion. And even though there's congestion control, it's a lot better if you can avoid it algorithmically up front. And so that's one thing that's important. The other thing in terms of, so I talked about numbers in terms of computational capabilities. The DPU cores that we use today are less powerful than the hosts, right? So don't give it too much work, right? Again, if you give it too much work, it'll show up because you're going to serialize and you won't get the performance and you won't. And what that means in practice, that especially in blocking collectives, we're careful. We don't just blindly put all the work on the DPU because it's there. You know, we take into consideration what makes more sense to do and continue doing on the host side, and what makes sense to do on the DPU. And so again, it depends on your algorithm, on what you're trying to do, and a variety of things. I mentioned before that the DPU has targeted acceleration engines. So those are things that aren't accessible from the host. And one of the things, so we don't have anything in particular that we're using right now for that. But part of my job is to look forward for these sort of things and see what sort of special engines do make sense to put on the DPU. So as I said, we have a family of products that's continuing throughout the year, just like just like the ConnectX or our CPUs, GPUs, and the like. One thing that's important, and this is sort of stating the obvious, but the DPU and GPU need to be in sync if they're both working on the same algorithm. They have to synchronize among themselves, so need to make sure you don't kill yourself with synchronization costs. From a network perspective, the DPU can be both a source and a destination of network traffic. So the data doesn't have to start and originate on the host. You can, again, it depends on your algorithm. So if you're doing some sort of aggregation algorithm, you may actually want to do part of it on the DPU, you know, where you have to land temporary data somewhere. The DPU is available. Take advantage of it, but again, don't do too much there because you'll harm your performance. Another important piece, another important capability that exists here is that on the Bluefield you can initiate network activity on behalf of memory that's not DPU resident. Okay, so to cause data to either be sent or received in main memory does not, from the DPU does not mean that memory has to live in DPU, in the DPU's DRAM. It can actually live on the host side of things, and there are these special keys called cross-Gavami memory keys that I'll talk about a little more in a while here, that let you basically let you post a work request on the DPU for data that's either its source or destination is on the DPU. Let's see. And the other benefit here is that the DPU is agnostic to the host, whether it's GPU, CPU, something else. The DPU doesn't care, right? When it comes to memory keys, it has these memory keys that it can use. It can run the algorithm independent of what's sitting above it. And there is a second capability that I believe exists in Bluefield 2, but there's actually independent hardware for it in Bluefield 3, parallel PCI lanes, is the ability to have their DMA engine that goes between the host and the DPU an additional DMA engine, I should say it that way. On Bluefield 2, I believe it shares the same lane, PCI lanes as your network traffic. On Bluefield 3, you have, I think it's 32 PCI, no, it's 16 PCI lanes that are that go through your ConnectX core and can go to the network. And you have additional 16 PCI lanes that you can use for traffic going between the DPU and the local host. So depending again on what sort of algorithms you're trying to implement, that's an additional data path that can be leveraged that does not impact the network activity. I will say those DMA engines do use a ConnectX hardware for address translation. So there is still some connectivity, but not a data path connectivity. An additional capability that exists is, as I mentioned before, the DPU has its own memory. Its memory bandwidth is a lot less than that on the host, but it's I forgot on the to go through the details on DPU 2 and on Bluefield 2 and Bluefield 3. But it has its own memory bandwidth, and so if you're doing things that require memory bandwidth, if you can move some of it to the DPU, that's a good thing. So again, I mentioned before aggregation algorithms. So we're starting explicitly to work on those sort of algorithms right now, and we're going to be careful again in terms of how we leverage this. We're not going to just say, let the DPU do all the aggregation, because it won't be able to keep up with the host, right? With the host-based algorithm. So this is an ability that that's available, and if you use it wisely, hopefully we'll be able to see performance improvements. I expect to. One thing that helps here, even though when it comes to network or network type of operations, even though the DPU is not nearly as powerful in a lot of ways as the CPU, your goal is not to break even with the host. All you need to do from a networking perspective is saturate the wire, right? So you don't need necessarily, it's always nice to have the extra bandwidth because it helps you depending on what you're doing. If you have to do data packing or stuff like that, it's certainly beneficial. But it's not, what you need is just enough memory bandwidth to saturate the wire and probably enough to do a few operations on the data as it's coming through, and then you can build a very nice pipeline, even the way with its current capabilities. So I thought I'd put a slide specifically on the cross-Gavami memory keys, because I know this is a capability that at least folks here at Ohio State are leveraging and are trying to leverage more. And so what this memory key is, it's a memory key just like any InfiniBand memory key. So for those of you that don't know, memory keys in InfiniBand are used to map between physical memory and virtual memory. That's how we make the DMA engines work. That's one of the ways we make the DMA engines work. And so every network operation has a memory key associated with it, giving the card the information on how to translate between the virtual memory addresses that it gets and the physical addresses that hardware works at. And so there's a special memory key or a new memory key that was defined when the concept of the DPU came about, which is called the cross-Gavami memory key, and it has to do with PCI. The naming has to do with PCI naming, and don't ask me to explain it. And so what the cross-Gavami memory key, as I said before, lets you do is lets you post network operations from the DPU side that will affect memory that's sitting on your local, on the local host side of things, right? You can still use regular memory keys. You don't have to use on the DPU with work requests if you're not trying to access to modify that local data, right? If you're trying to do yeah, that's sufficient. But what this lets you do is this lets you move data to and from the DPU without moving data. And it leverages the fact that we have a common HCA that serves both the host side and the DPU side, and so it's really a translation issue of being able to access that memory on the DPU side versus the host side. So it's translation, and of course security is a big deal there. You don't want to expose big security holes in terms of network activity. So one of the things that the first version of in Bluefield 2, the first version of these memory keys, the way they were defined was through firmware. Firmware was modified, so every time you wanted to create a memory key, is a very expensive, a new memory key, a new cross-Gavami memory key was a very expensive operation, probably 3 orders of magnitude more expensive than just your standard host-only memory key. And it had to do just with the fact that we had early generation of hardware. So it had to do with well, the details probably don't matter. Bluefield 3, that's been rectified. So there's been a hardware change in data structures associated with memory management that allows the Bluefield to take advantage of the same high performance memory registration capabilities that the host can. There's a capability called it's called UMR. It's a way to map. To create memory keys very fast. It's a hardware way to create these memory keys versus a firmware method that you typically get if you use your IBV regmr routines. For those of you that are familiar with them, and so that along with some aliasing tricks associated with using UMR again to lets you get back to a cost of creating memory keys on cross-Gavami memory keys that are very similar to those of your host side activity, host side memory keys. They're hardware accelerated and they're fast. So for those of you that are developing algorithms using cross-Gavami, this capability exists. And I can be more than happy offline to talk about the tricks to speed it up more than just the first step in the memory key creation. Oh, the computer's about to restart. Let me snooze it. Okay. Now this responds. So those are the details on hardware, and what I want to go through is now some slides about the infrastructure, the communication library infrastructure that we're using, our development. We're doing our development in this context. So there is and this infrastructure, this library, this open source collective communication library is called, as I said before, UCC, and I don't remember what UCC stands for. It's in the same consortium that UCX is underneath. They both come from the same consortium, and so this is not an NVIDIA proprietary library. This is an open source library. Although the algorithms, some of the algorithms that we write do not go to the open source. So a bit about NVIDIA's HPCX to put the software stack into perspective. So NVIDIA supports an HPC communication stack via a product we call HPCX. It has both MPI and SHMEM implementations. It's based on OpenMPI. It uses UCX for point-to-point optimizations, and UCC for collective communications. It also has the support for HCOL, which is NVIDIA's proprietary collective operation library, but that is being deprecated, moving things over from HCOL to UCC, which also turns out to, since it's a second generation, there's some optimizations that are going on in the process to make it more efficient. It supports, in addition to just standard host-based or software-based collective communication, it also has support for both nickel, so NVIDIA's collective communication library that's targeted at GPUs, and the network reduction capability known as SHARP. And it leverages, again, the in-network computing infrastructure with SHARP and with the new collectives that are being developed. So a bit about UCC. So it has a unified collective stack. It's not aimed just at MPI. It's not aimed just at, I'll say, scientific HPC, because machine learning is also part of HPC. So it's targeting both our legacy HPC as well as machine learning type of workloads. It has a unified stack in terms of network support. So the stacks that I know of that are currently supported, and I'm sure there are probably others, I just don't keep up with UCC personally. So it has support for InfiniBand, of course, for shared memory, for TCP, so you can run it on your laptop and do development on your laptop. And I'm pretty sure it has support for Slingshot via I forget how they get that, but let's see what else makes sense to say. Okay, it's modular. So like any framework, you can add new capabilities. So we're over time adding support for additional capabilities. So we don't have to have full support for all collective communications within UCC to make it usable for your communication libraries like MPI. So it's just like any other collective in OpenMPI, for example. It can pull collectives from different libraries. So we leverage that. From an architecture perspective, I have a very, very high level picture of UCC's architecture, your standard software architecture pictures. The most important, and if someone has questions, I'll be glad to answer, but I'm sure your eyes will glaze over, and you've seen so many of these diagrams, you probably don't want any details about them. The most important thing from my perspective in this talk is the green box. The green box here represents UCC from a software perspective. The places where changes are made to support the DPU is within a layer called the TL. There's a UCP layer that it's modified to support DPUs, and there's from a implementation perspective, there's a new transport defined, which supports the DPU, right? So it's really not targeting any new hardware, just from an architecture perspective. It's a different architecture than, for example, your verbs. It's very much akin to UCX or Nickel or so, that build on top of hardware capabilities algorithmically. So a bit about the infrastructure that we use, and we've shared this infrastructure with other people. There's no reason for us not to share it. You know, to help people get off to not take a year to be able to build your infrastructure, so you can start experimenting with these things. And so we've certainly given this infrastructure away in some of the workshops that we've had around the world with respect to offloading these capabilities. We're trying to transition away from it to the formal infrastructure that NVIDIA supports, which is DOCA, which means we don't have to support it anymore, and it goes to standard support. And so a bit about the terminology used within this infrastructure. So the name of the infrastructure is Mimosa. Again, don't ask me what Mimosa stands for. I don't remember. And it's a library that's targeted basically at supporting these offloaded collective communications. So there are a set of APIs. I'll talk about a few of them. Yeah. So one of the basic architectural components of the implementation is that we have service processes that run on the DPU. They could have been service threads, but the person that implemented this preferred processes. So we have service threads that basically continually run on the DPU. You attach the service thread when you want to use it, and they provide services to the collective in this case. And we can have, and actually do have, multiple service processes running on a given DPU. This gives us the ability for parallelism, we have, in Bluefield 3, we have up to 16 cores running on the DPU. So we could have, in principle, up to 16 cores, up to 16 service processes running on the DPU, serving all the host side MPI processes. And so these service processes recognize an API that we've defined, that's Mimosa, that give the ability to synchronize and pass messages and communicate between the host and the DPU, and between local hosts and remote hosts and the like. So the local, in terms of DPU access, really the only way that the major way that, actually the only way that the DPUs differ is your local DPU is physically connected to your host through a PCI bus, so it's close. It doesn't have to go over the network and contend with other processes, but it can also interact, and it does interact with remote DPUs also. So a lot of when we exchange data, when we have, think of your simple ring algorithm that you might do to implement an all-to-all large data. We actually drive that entire collective from the DPU for the large data. So the DPU gets a large set of work, and it implements the ring algorithm. So it sends data, so it initiates data transfer. We do reads because it lets us control how much data gets put on the network. And it lets us do a lot better job of synchronizing and reducing effects of congestion. It will read data from both local. Well, it won't read local because we don't use the network for local traffic, but it will read data over the network. So it's not restricted to the DPU. Isn't tied so much to the local host that it can't do any work for remote processes. We also have the concept of an endpoint handle, just like UCX does. And actually, that's where it comes from, because all our communications are layered on top of UCX. So the goal of this infrastructure is really to provide what we need as a development team, and then if people want to leverage it, they're more than welcome to, and is to a set of primitives that we can use for different different collectives, for example, just your standard software engineering type of workload. So the algorithmic portions of it are really defined on a per collective basis, right? But we have a common infrastructure that we use. This is nothing special. This is what everyone does, right? We've just defined it for what we need, the sort of operations that we need when the DPU is involved, because they're different than what's necessary when you have host-only operations. The offloading, as I mentioned before, all the offloading services run on the DPU. We offload collectives, and as I said, we split the algorithm implementation between what happens on the host in the context of MPI and what happens on the DPU outside of the context of MPI. So we need to recreate some context, some MPI context on the DPU, so it knows, so that the algorithm there is run correctly. And actually a single service process has to recreate that for a variety of different local ranks and all the effects that come when you have local MPI ranks. I'm sorry, again, I'm talking MPI, it's not restricted to MPI. And all the extra management that happens when you support multiple communicators. One thing that's a bit tricky here is because you have that context, a common context within a given service process for multiple MPI processes. The fact that you have, so MPI defines, well, MPI has an undefined entity that's used for in communication called a communication context. The standard doesn't define what it is, but I think probably everyone implements it as an integer. Within an MPI, on the host side, within a local MPI process, you can guarantee uniqueness of that. You can guarantee that you'll have, if you have the same given communication context, MPI communicator context, you won't have collisions between communicators. When you're running in a common context, that's no longer the case. The fact that you have, both processes have context one doesn't mean that they're in the same communicator. So, let's see. In terms of communication key concepts, we have offloading engines that basically run the in our case, collective communications. We have execution context that again create context for a particular host side process that's being served. We have events and notifications so that we can respond to new information coming from the network, new instructions coming from wherever they come for. And we also have an endpoint cache for maintaining our cross-Gavami memory keys, just like MPI implementations like UCX maintain a memory key context to speed up network memory access to cache those sort of addresses. The same thing happens here, but we have to create that on the network side. Let's see. So what's necessary from an offload perspective is to be able to identify when you get data over the network, what algorithm it needs to serve and for who. This is no different than happens on the host side. There's just a little more complicated because you're serving multiple entities, at least the way we do it at a time. And I should say, I should make that comment here. We could have done this model where we had one DPU model per MPI process on the host. That would have worked. We would have oversubscribed the DPU, and we would have had a lot of problems with context switches, a lot of costs there. And so this is why we did not take that approach and took the extra complication to deal within that within the DPU to deal with that with that extra complication. Obviously, need to implement DPU side algorithms, and no need to say more there. Again, from an architecture perspective, we have each host, each local process has a local service process. Each local process has a local service process that serves it, process on the DPU, and those DP. And from a communication management the perspective, two things that we can do here. One, the service processes can pass work to each other, which makes sense in some contexts, especially if you're trying not to block. And it can also communicate both. They can communicate both locally and remotely. What's worthwhile saying about the offloading engines? So the offloading engine is where okay, I see what, yeah, so the offloading engine is split between the DPU and the host, right? Just like we split an algorithm between the DPU and the host, the offloading engine is also split between them. And so the way, to give you a bit of context what this means when we talk about this, so it's not opaque to those of you that are doing this sort of work. If we have a blocking, let's say all-to-all V, it's more interesting, all-to-all V operation. We don't blindly send all the list of offsets and lengths and the like to the DPU, and expect the DPU to serve all to handle all the communication, all the coordination. We split the work between medium-sized messages that would be sent eagerly, for example, when point to point, and the larger messages that involve typically a rendezvous protocol. So we will have the DPU handle the rendezvous type of messages, and the host side handles the shorter messages that would be sent eagerly in any case. And so that's just one example of why you would want to split the algorithm between the host and the DPU. Let's see. I'm trying to scan through here and see what's interesting to say. Yeah, so just in terms, the only thing I think that's really worthwhile saying right now, rather than is each of these engines have an init and finalize capability, so you can define your own engines. You can extend the service to have offload engines for new capabilities. Again, there's things around the execution context, which is the context in which all operations happen. That is, on the DPU side, we have to recreate an MPI context for a specific process. And there are some APIs used here for defining the basic capabilities that are necessary. And again, these are things that just for a high level overview of what's available. So this infrastructure obviously has been put together to be extensible and will eventually make its way over to our product. Events and notifications, these are probably, I won't go through all the details here in terms of how everything happens, but the most interesting things here are just like in any sort of network type of activity. You know, when data comes in on the network, you need to be able to pick it up, you need to be able to parse it and know what it's telling you to do. And you need to be able to progress whatever algorithm's has been requested with the appropriate collective operation and like. So this is what events and notifications, the event and notification service is designed to do. So what it basically does is it provides that capability, and if you're interested, you want to use it, you don't have to go and recreate all this infrastructure from scratch. It takes a lot of time. So as I said, it took about a year to implement and robustify this sort of capability. And so, like any software product, you want to robustify it. So from a library perspective, from a distribution perspective, we have two different libraries. We have the host side library for the offloading library that sits within the UCC stack. So this is, if you're using UCC, this would be necessary. And then we have an independent DPU side stack or library that provides these services. And as I said before, in our case, we use UCX for all communication. Not that we couldn't write it from scratch, but UCX took several years for quite a few people to write. So there's no reason to write this stuff from scratch. Might as well leverage what's already been done. Again, this is so as a service, it has the way to map from a rank to a service process, so that you can, again, you can target the appropriate service process corresponding to the MPI process that you're trying to serve with a given or you're trying to address with a given message. So it has all the capabilities necessary to do that translation. Yeah, that's probably the most important thing to say there. So just as a closing slide, to give a picture of how this all comes together, we've taken a piece here of a collective algorithm. Just one piece. This isn't a full algorithm by any means, and to show how we take this, how we use this. And so this is intended very specifically for the portion of the algorithm that we're offloading to the DPU. So in all our algorithms, when a process arrives when an MPI process is called, let's say MPI all to all V is called, if it's appropriate, that is, if it's the portion, if it has the data type that we'll want to serve on the DPU, it will send what we call a host arrived message to the DPU. And so that host arrived message encapsulates everything that the DPU needs to know from a metadata perspective on the operation. So with an all to all V, it would pass your lengths, your offsets, and that sort of information to the DPU. It would also pass your memory key, your Kraskavami memory key to the DPU. We map everything in one step at the beginning of the algorithm to be most efficient. The DPU picks up, gets that host arrive message, looks at it, decides what algorithm to run, looks to see what to do with the data, and then it will start the data transfer process. So in terms of for example, an all to all V, the DPU will see that it needs to send a message to some remote process. So it will send to that a small message, one of these notifications, to the remote DPU, telling it, I want you to send the process on the host side has data for you. This is its characteristics, and then that remote DPU will use the Kraskavami memory key to read that data to the and have it land in the memory of the local host. In this case, actually, you don't have to use the Kraskavami memory key. That's just the way the implementation was done. For this particular thing, actually, you do need the Kraskavami memory key for your local memory, not for the remote memory. And the data gets transferred, and when completion happens, so completion notification comes to the remote DPU. The remote DPU will send an ACK back to the DPU on the other side, and eventually, when everyone is done with the operation, the DPU will notify the host that it's done. So for the entire duration of the operation between host arrive and host done, there's no communication back to the host at all. Direct. I mean, there are reads from it, stuff that's hardware level, but nothing software. So that's it.
We do have a question in the chat. So this is from, okay, so hold on, he's updated this. So he says, oh, sorry, two different people. Okay, so the first question is from Mohit Sharma. Can you define MPI run with some possible features or flag?
So currently, what we do, we don't have an MPI run for this. We have scripts that we use. It's on our list to implement that, so it's easy to use. Right now, all we're using are scripts. So there's nothing preventing it, but we just haven't done that yet. So the answer is it's doable. It's yes, we can do it. No, we haven't done it.
Okay, and then the second question is from SN Banerjee. He says, nice talk. How do I optimize the traffic in embedded mode using DPDK, considering huge TL buffs is mounted and set to Echo 4 redirect output / system kernel huge pages, and the x86 host server OS used is CentOS 7.5 with Bluefield 2 as 100 gigabits per second rate. The iPerf shows poor stats.
So the best thing to do, so one, we don't do my team doesn't do anything with Ethernet when it comes to packet processing. So there is certainly an effort that's doing this, supported through DOCA. And the best thing to do is put them in contact with those folks that can help them. I don't do anything with DPDK, so I couldn't start to tell them how to tune DPDK. but there's been a lot of effort gone into it there.
Okay, and I've got one more from an anonymous attendee. What is the difference between Google Cloud TPU and NVIDIA DPU?
Good question. I don't know the TPU. So I don't know how to answer that.
Okay. All right, that's all I got on
Actually,
chat.
the tensor. So the TPU is aimed at, now I do remember what it is. So the TPU is really aimed at doing tensor operations, right? So you could run tensor operations on the DPU if you wanted to, but you probably don't want to do it because it's not targeted for that. It's not, yeah. It's not the TPU is, that's what its job is. And so it's highly optimized for that. Yes.
I'm curious, can the AGVMI keys that you generate kind of in the first step of the batch, can those persist across collective operations, or do the keys need to be regenerated at the start of like every op?
No, just like any network activity, any sort of, if people typically build infrastructure to support using them across generations, and we actually rely on what's implemented. It's not there in UCX to do that.
Okay.
So yeah, otherwise you're going to pay a lot of cost, as you said. Defining as you know probably firsthand. Yeah. Creating memory keys is very expensive, yeah. And so you want to leverage them across multiple operations.
Okay.
This last example assumes you have one DPU rank per CPU rank.
No.
No.
No. I'm sorry.
This example shows the rank 1 DPU, so this
yeah,
is
just,
one process per
yeah,
CPU
it just picked, you can have as many ranks as you want running on the host. We just picked it to go between two, to give an example of what would happen between two. So a given DPU could be servicing several of these in parallel, right? So, but this example just shows what a single algorithm would look like, what a single algorithm would do.
Okay.
So yeah, if it's not a useful way to implement it, if you have to restrict the number of that's
what I was thinking of.
So that's why I said several times is that a given service process serves multiple MPI ranks in the case of MPI.
Yeah.
It didn't have to be implemented like that. You could do one process per one MPI rank, but then you would have the problem of you'd have to do context switching all the time, and that would just destroy your performance.
So isn't it a big issue when we have processors having 128 cores or maybe more than that?
No, as I said, I assume in the implementation that I'm going to have 10 times more compute endpoints on the host compared to what I have on the DPU. Now, in some cases, maybe it will harm it, right? If there's so much work coming from the host that you can't keep up with it, but then most likely you would have the host sitting. The only instance that I can think of that's relevant there, off the top of my head, is if every process is trying to send small messages as quick as they can.
Yeah.
I wouldn't offload that to the DPU. That doesn't make any sense.
Yeah, right.
So, yeah.
Any other questions?
Thank you for the talking. And the question is, if I want to utilize hardware accelerator on the DPUs, is that only way I can use that accelerator is where the Docker SDK, or is there any like lower level APIs or drivers I can use?
So this is a piece of hardware. You can write whatever code you want to run on it. We do not use Docker. We do not use Docker because Docker isn't ready yet for what we need. What we're doing will eventually run into Docker, could go into Docker. So if you want, you can write everything from scratch and run it. That's probably not recommended. But that's also one of the reasons I've mentioned that we're more than willing to share our stack with other people to use, so you don't have to go through that year of writing your own software stack, just to be able to do experiments. So.
Oh, okay. So what is the lowest supported API or driver, the Offload, or like if I want to write from scratch?
From scratch, yeah. If you want to write from scratch, you would do it, and you would sit on top of Offload.
Okay.
But from scratch, you have to figure out how to start a binary on the DPU, right? And not get stuck by some of the restrictions that exist for the hardware. So, I mean, in principle, you could write an MPI run that would put processes on the DPU, start processes on the DPU, just like it would on the host. We decided not to. That's what was done early on. So I had a PhD student at UCL and University College London. That's what they did. It's not a good model if you're trying to change applications, because you have to change communicator definitions on the application side. So there are a lot of things you can do, but there are probably a smaller set of things that you should do, depending on your goals.
Yeah. Okay, thank you.
Okay, so might be now we take a break. Thanks again. Let's give thanks to Rick.